we can use some fairly straightforward geometry to find the location of the image formed by a light from an object passing through two types of lenses. A converging type of lens in which parallel rays of light are brought to a focus at the focal point, and a diverging lens, which I'll talk about in the very next labeled section. Now, in order to find this using geometry, my recommendation is to either carefully measure out paper with a ruler, or hey, go ahead and get yourself some graph paper somewhere. It'll make life much easier. Now, let's say that I've got two objects I'm going to look at a particular image seen as seen through two different lenses. These are both converging lenses, but they have different focal points. And the focal point is where all that light coming in parallel into the lens, any beam of light parallel to this line called the optical axis that enters the lens will pass through that focal point after it is refracted on its way out. Now, there are infinite numbers of rays of light, as we talked about at the beginning of the chapter, that pass through this lens. As it turns out, there are three that are easy to track and easy to follow. If we use those three, our life will be easier. Now, let's look and define those three. One, it enters the lens parallel to the optical axis. Let me make sure that I'm catching all of this on screen. The ray of light will then pass through the far focal point. So it comes in parallel to the optical axis and passes through the far focal point. The second ray passes through the near focal point and leaves parallel to the axis. So it passes through the near focal point and leaves parallel to the axis. Because if I have like the path of light going through a lens or going through an object from, if I have, here is light that comes in parallel to the focal point, parallel to the optical axis, all passes through the focal point. Then light passing through the focal point will leave parallel to the optical axis. And the third one is straight through the center at the optical axis. That passes through undeflected. Well, really, if I have a solid object of glass, and I have a light ray enter in, then what's going to happen is that, sure, it's going to get refracted at the first entry point, then refracted again at the second entry point. So it's going in and out, despite how badly this is drawn. It's in and out in the same direction. It's shifted just a little bit because of the thickness of the lens. That's why if we're going to use here a very thin lens, notice that the thinner this lens, the less shifted. The angle is still the same. So you can try and draw that so that is, the angle is still the same, but as this gets thinner, that shift gets thinner. So there is one ray. I can simply draw as passing through the center. Now, all of the rays in will all of the rays leaving from the tip of that point will pass through the plane of this lens, or that pass through the plane of this lens, will all be brought to a focus at that point. So as long as we have three, and we know where those three hit, then hey, we're good. We know where all of them hit. And these three are easy geometrically to do. Now, one problem that I see is sometimes people think, okay, that's how converging lenses work, and then they always draw it like that. Don't just memorize this and draw it like that. Remember these rules and use them, because suppose I'm inside the focal length, okay? It enters, one ray enters the lens parallel to the optical axis, then leaves through the far focal point. One ray is on a line with the far focal point. Actually, that might be, say that's it. It leaves parallel to the axis. Oh my gosh, that's outside of the lens. Can we still use it? Of course we can. These are just three model rays. It doesn't matter if they go through the physical lens. We're just trying to find out where the heck things meet. Then the third one passes straight through the center. Now, on this side, even if I were to draw those carefully, and I'll try and make some nice, friendly illustrations to help you out, along with the on graph paper that I'll simply scan in. Looks like these rays never meet, and they don't. But if you track them back, if you're standing on that side of the lens, looking through the lens, then there will be a point where those rays, scan it back, all seem to come together. Now, here, this image is flipped compared to the original object. So this image is inverted, where this image, which has the same orientation as the original object, is upright. This one's a bit perhaps more involved. In this case, if I were to put a sheet of paper here, then a bright object having light pass through the lens will form an image on that sheet. So this is a real image. In this case, I can't put a sheet of paper behind the object and get an image of the object. I only do if I only see the image if I'm looking through the lens, and it's like, okay, there's the image on the far side of the lens. You can't put anything there to catch it. If you take like a magnifying glass, look at something close up, then it's like, oh yes, my hand looks very large. It looks like the image of my hand is like, right here. But I can't put a sheet of paper there and get an image of what I'm seeing through that magnifying glass. So that is a virtual image.